Hello everyone and welcome back to Indian Genes. So as promised, this is an Indian Genes exclusive episode and comes to you in two parts all the way from CERN. My guest today was part of the team that successfully identified and discovered the Higgs Boson, the elusive God particle as it was called, and a discovery that went on to win the Nobel Peace Prize in Physics in 2013. He is a postdoctoral researcher with the Atlas Group of Duke University and based full-time at CERN, currently working on the largest and most expensive experiment in human history. He completed his PhD at New York University in 2014 and is currently a postdoctoral researcher with the Atlas Experiment Group of the Ohio State University. He has been a guest on NPR's Science Friday, participated in documentaries on the BBC and the Discovery Channel, and talked particle physics with the New York Times and Wired. In addition to his ongoing research, he is dedicated to making particle physics accessible to all and has communicated science to the public with Symmetry Magazine, US LHC, the Science Museum in London, the Institute of Physics, the World Science Fair, and on the web. This conversation went on for nearly 3 hours, and I would sincerely like to thank him for what I'm going to be presenting to you today. And we will be releasing this in 2 episodes for obvious reasons, as there is a lot to take in here. These 2 episodes are really a testimony of my guest's drive, commitment, enthusiasm, and every quality you would look for in someone trying to answer some of the biggest questions in science. His energy is infectious, and as you listen to him, I do hope that you are inspired just like I was, and marvel at the passion he has to his cause as he breaks down every topic to its smallest component to help us better understand and grasp its principles, much like what he is currently doing at the LHC with atoms. I now proudly present an education in the form of a conversation all the way from CERN with Dr. James Beacham.
Hello, Dr. James Beacham, and welcome to Indian Genes. It's an absolute pleasure to have you here.
Well, it's my pleasure to be here. Thanks.
Thank you, James. And we were just talking some time ago and to some of my colleagues here in the studio as well, and the moment I told them that I would be speaking to Dr. James Beacham, everyone here is quite excited. There's a lot they want to hear from you, about you. You're working in a great place. You're in CERN. My listeners have also been introduced to you. So there's a lot we're going to talk about. But before we get there, James, I want to quote something from a politician. And apparently this is what happened when CERN initially put out a proposal for finance. And the quote from the politician was, "If you can explain in language of a politician what the hell you guys are doing out there, you can definitely have the money." So I'm going to say, I'll change a couple of words there, and I'm going to say, if you can explain in the language of a common man what the hell you guys are doing out there, you'll definitely have our support. So let me leave it to you, James.
Well, thanks very much, and I'm extremely happy to be here. And I think that, part of my whole goal as being, kind of a public-facing scientist, because, I'm a full-time researcher here at CERN at the largest experiment in human history, the Large Hadron Collider. But, I do that full-time, sort of my day job, because I love it, because the research that we do is endlessly fascinating and too many projects, and I love it so much. But I also take a lot of time and kind of make sure that the public gets a chance to understand what we do, because at the end of the day, my research really is your research too, and that's one of my goals, is exactly to do what you do, or what you said, is to make sure that we can break down what we do into pieces that people that are not specialists will understand. And so I wouldn't even call them the common man or the common person. I would just call them non-specialists. I would call them, the only thing that separates me from you is that I, did 6 years worth of quantum field theory calculations in graduate school, right? At the end of the day, we both have deep down inside, deep down in our bellies, in our hearts, in our souls, we have this kind of curious, kernel of childlike curiosity. And if I can get down to that one little kernel and reignite that, then we can find common ground, and then you get a better sense as to why we bother to do this type of research at all.
Right. And I think a lot of us would also want to know what it is like for a day at CERN with a scientist like you. But before we get there, James, how did you get interested in this? Because I think you also are interested in film, and you did a course in filmmaking. That's quite interesting.
Yeah. Well, let's put it this way. I've always been obsessed with the edges of knowledge. Let's put it that way. I've always been obsessed with the very edges of what humans can know. And I mean that in the following sense. So particle physics is the place that you find yourself when you're that curious little kid who never accepted that's just the way it is as an answer. So, if you're a little kid and you're looking up at the sky and eventually you ask your father or someone, like, why is the sky blue? And if the answer comes back, oh, that's just the way it is. If you're the particle physicist, you don't accept that as an answer. You go, wait a minute, that makes no sense. There has to be an answer. And so you go and ask someone else. And if they don't know, then you go to the library or you go to the internet and you find these things out. The particle physics is just the place you go when you always are obsessed with finding out the underlying structure behind anything around you. And if you keep asking this, the kind of the how and why questions behind the how and why questions, eventually you find yourself in particle physics, because that's really the edge of what we know right now. And so as a little kid, I really was the kid that would just ask the questions and always be dissatisfied with the answers and want to know more and more and more. And so when you find yourself as a little kid in that sense, of course you're drawn to the techniques of science, because science is this wonderful, glorious process, right? I mean, I think everybody in your audience knows this already, but it's good to remind ourselves that science is not a list of facts, right? Science is a process. It's a way of thinking about the world. It's a way of asking and answering questions in a robust way that we can come to reliable, repeatable conclusions about the way that the world works around us. And so when you get into science as a little kid, it's like if you're that curious little kid and you're lucky enough to be in a place where you have parents or guardians or people around you to encourage your curiosity, or at least resources that you can appeal to. I was very privileged to be in a position like that. Then you find yourself, being drawn to the methods and the techniques of science. And so when you get in there, suddenly the entire world opens up. People before you had gone into so much detail to put together this methodology about examining the world around us and exploring the hidden structures of everything around us. And you find out about biology. You find out about evolutionary biology by natural selection. You find out about chemistry. You find out about weather patterns, about oceanography, about dinosaurs, about paleontology, all these things. And eventually you find yourself asking about both the largest things in the universe and the smallest things in the universe. So if you stare up at the sky, you're looking at the stars and galaxies, you start wondering what those are. How far away are they? What are they made of? Mm-hmm. And if you go the other direction too, you go as small as you possibly can. So if you're in biology, that's fantastic. And I remember biology class was so fascinating to learn about chromosomes and protozoans and all these things. But then you ask the question, what's below all of that? And so then you get to you get to molecules, and you start getting into chemistry and the way that atoms form together, and you think, what's below that? Mm-hmm. And then you get down to atoms, and you realize that you have nuclei and electrons. You say, what's below those things? For example, an electron. We get to an electron and ask the question, what's smaller than an electron? Is there anything inside an electron? And the answer is, we don't know. Mm-hmm. And that's the place. If you're a particle physicist, that's where you find yourself, because that's the edge. That's the very edge of where our human knowledge currently ends. And that's where you're like, that's where I want to be. That's where I want to study. And so as a kid, I was just sort of drawn to these very kind of, I guess I was sort of an extreme kid, in a way, because I wanted to know the very kind of the smallest possible thing and the largest possible things, and how these kind of things fit together. By the same token, I was also really fascinated with the way that with the sort of the hidden social structures that would also that were all around us all the time as well. So, for example, why do people act the way they do? Why do humans organize themselves in societies the way they do? And also, what are the kind of hidden emotional and psychological, and also kind of like formal or aesthetic things, rules that govern everything around us? And that led me to film. I was also really interested in cinema as a means of exploring very complicated ideas, social, emotional, political, these kinds of things. So I was drawn to these two kind of things simultaneously as a little kid. And then as I got older, I just realized that I wanted to study all these things, and I figured I would just keep doing what I wanted to do until someone held a gun to my head and told me to stop, and that's never happened. So I did a bachelor's degree in filmmaking, but while I was making my own films, kind of experimental art pieces, I realized that I was still obsessed with particle physics, and I realized that I was doing myself a disservice if I didn't study it formally. So I got a completely separate bachelor's degree in physics and math, a double major, and then I did my PhD in physics, and now I moved directly from Manhattan to Geneva, Switzerland, and now I'm here working at the largest experiment in human history, trying to understand the basic, most baffling puzzles of the universe, and it's quite extraordinary.
That's a beautiful story, because a lot of my listeners are university students and kids in school, so listening to what you've just said, I'm sure they are going through all of that right now as well, and trying to figure out which direction they want to go. Having said that, James, I think this is a question that I've got people asking me to, if I get a chance to speak to you. What is it like for you in a normal day at CERN? How do you go about your actual day, and how do you work through all the experiments that you're doing?
Yeah, so first of all, CERN is an amazing, awesome place, and it's very unique amongst all the places that I've ever, worked in my life, because my trajectory, I realized, was a little bit weird and atypical, and so along the way I did have some kind of fits and starts, and times when I was, working kind of regular Joe jobs and little things like that, trying to pay the bills while I was going to school and doing things like that. And so I've worked in a lot of different places, and CERN is a really unique place. And in fact, I highly encourage everyone listening to come and visit at some point, and you absolutely can. It's a lot of fun. You can organize like a school trip or like a company trip or something like that. You can come and you can take a tour, and you can actually go 100 meters underground and you can see one of our big experiments. I know we're getting ahead of ourselves here, but that's that's definitely something that's accessible to the public, because our research really belongs to the public. It's supported by public resources from all over the world. But a regular day here at CERN is both. I have both good and bad news for people that are that want to know the answer to this question. The good news is that it's great, right? Because it's a very unique place, because you have thousands of people coming from around the globe to this one place to work on these projects that are really just because we're curious, just because we want to know more about the nature of the universe, the way that the basic rules of the universe. Not because none of us are here because we're going to make a profit, because we're not. None of us are here because we're going to get get rich, because we're not. You can't make a product out of the Higgs Boson particle, right? And if we discover dark matter, you're never going to be able to make dark buildings out of dark matter. So the reason we're here is strictly because we're curious, and that makes it a very unique place. It's a self-selected group of people for whom this was the highest goal, for them to come here to participate in these big projects that are researching things that are bigger than all of us individually. We really have to act collectively. So a regular day here is fantastic, because I get a chance to interact with people from all over the globe, and I have meetings where we discuss projects and and little sub-projects, and I'll be sitting in a meeting in a room with me from the United States, and someone from Norway, someone from South Africa, someone from Canada, someone from Sao Paulo, someone from Tokyo, someone from Mumbai, someone from Beijing. So it's like everybody from all over the world comes to this place, and it really is necessary for us to do that, because when you do that, I mean, as you know, diversity is the greatest strength that any organization can have. And for science, it's absolutely essential as far as I'm concerned, because when you have people from different perspectives and different backgrounds, ethnicities, languages, mother tongues, things like that, they really come and bring new perspectives on the research. They really do. And so if I approach some research project with one particular set of assumptions and experiences, that will get me to a certain point, right? But then if I get in a problem, it's very useful to be able to submit it to the group, and then somebody else says, did you think about this and this and this? Because their different perspective affords a totally different way of looking at things. So that's really a fantastic thing. It's also a lot of fun in terms of day-to-day, because we get a chance to work on electronics projects. We get a chance to do a lot of coding. So that's because a lot of what we do is sort of just day-to-day stuff. So that the good news is that it's a lot of fun to work here, and there's always stuff going on. The not so ecstatic news is that sometimes this is just another workplace, just like anything else. So no one should think about this, CERN as. I think sometimes when people, because of the reputation that CERN has, sometimes people have this idea that it's a place that's kind of like the Facebook campus or the Google campus, where it's all like primary colors and like there's open office plans and everybody is sitting on the bouncy ball chairs and like doing yoga, and playing ping pong, and that's not really what's going on here. This is a physics laboratory.
So you guys are seriously working 24 hours?
No, not 24 hours. No. Well, that's the other part, is that there are some people that are pretty hardcore and they work pretty long hours, but that's also not really the overall ethos. Honestly, there's a lot of people here that they recognize that this research is best done, it's best served when you find the proper work and life balance, right? Because if you're constantly working 18, 20 hours a day, that's great if you're working on some kind of small thing like a short-term project. But long-term, it's really going to reduce your ability to think broadly and in new ways about your project. You know what I mean? It's like if it's sort of this notion of the law of diminishing returns. If I stay up for 48 hours in a row. Just by pushing myself farther, staying up longer, I'm not actually going to be doing anything better, because my ability to do things is way less efficient than it was if I just took some sleep.
Right.
So no, we do not work 24 hours. And in fact, there's because it's such a unique location. Geneva is a beautiful place. It's right in the middle of Europe, so it's highly accessible to other places, all around Europe. It's also really close to a lot of great skiing. So I know a lot of my colleagues, they really enjoy going skiing on the weekends. So there's it's more or less it's about finding the proper kind of work-life balance for you as a scientist here. And some people do that better than others. But yeah, so we do not work 24 hours a day. Some people are kind of extreme and they like to work a lot. Some of us work too much and we try to cut it down. But at the end of the day, you realize that this project, again, the things we're working on are collaborative by nature. They require, dozens, hundreds, thousands of people. And so it's okay if you schedule things, if you arrange things so that you do not have to work 24 hours. You can instead work your part, and then you can, pass on your work and, what you've done to your other colleagues, and then they can get back to you on the stuff they're supposed to work on, and then it kind of goes in iterations like that. So yeah, it's a fun place. It's interesting too, because I'm looking out my window right now and I'm reminded of how kind of utilitarian it is here as well.
Yeah,
so I'm also because as somebody that also has like sort of an art component of my life, and I have a lot of friends in the art world, and I did a degree in cinema as well. This place is I also like architecture quite a bit, and if you look at the architecture just just looking at it from a distance, it's very, very, very much like a factory, or very much like like an old school like a construction site or something like that. Yes. It's really because it gets at the heart of, just to finish the thought, it gets at the heart of, why it is that we do this research. Why, what's the sort of person that is drawn to particle physics research. Particle physics, again, what we are is we have to be, especially as an experimentalist, right? Because I'm an experimental particle physicist with this ATLAS experiment, one of the two the two experiments that discovered the Higgs Boson particle in 2012. And, we have to be almost Swiss Army knives as thinkers, as scientists, because we have to be, at certain parts of the day in our career, we have to be electronics people. We have to really do very low level, studies on electronics and make sure that they all work together, and different types of, cathodes and anodes and like these kinds of things, and understand exactly how the detector pieces are working and debug things that way. And other parts of our career, we have to be, coders, programmers. We do spend a lot of time programming, primarily we use things like Python and C++, but we basically use any language we need to get a certain job done. We also have to be, people that put together presentations. We also have to be, we have to be able to manage small groups of people. So, at the end of the day, what we are is we're hackers. We're hackers of the physical world. And hackers, as you know, I don't mean that in the bad sense of the person that's trying to, hack into the power grid and shut it down, for some kind of threat, something like that. What I mean, or trying to, steal money from a bank account. What I mean is a hacker is a person who is really just, they look at what problem is in front of them, and they try to find any tool that exists anywhere to get the job done. right? So for coding, this is, if you have some kind of coding problem, you don't just say, well, there's not a Python function to do what I want to do, so I'm going to stop solving the problem. No, you find something to do to solve the problem, or you create it to solve the problem. And for particle physics, it's very similar to us, except what we're trying to solve are sometimes completely ill-defined big mysteries of the universe. Why are galaxies spinning faster than they should? Where's the missing 95% of all the stuff in the universe that's driving the universe's expansion and the way that the galaxies move around? These questions are sometimes completely ill-defined, and so you say, okay, well, what tools exist to solve this problem? And none of them exist, and so you say, okay, let's build a 27-kilometer circular tunnel 100 meters underground the border of France and Switzerland, and put a bunch of complicated electronics and magnets in there, and try to design something that'll help us answer this question. So in that sense, particle physics is we're very much like hackers of the physical world, and it's a lot of fun to interact with people like that all day long.
Right, and there was also, I think, a couple of days, or maybe yesterday, a report about an explosion, or probably they say it's one of the biggest explosions since the Big Bang. Have you been involved or heard of it, or what's the latest on that?
No, that one, in fact, I just read a news story about it, because that is, if we're talking about the same thing, there was a news article by some researchers in, I forget where the collaboration was located, but anyway, they have, it's mostly astronomy. The people that look for those, that see those kinds of things, they are using very complex satellite data that they basically observed a gigantic gas cloud somewhere, what is it, like 100 million light years away or something like that.
Exactly.
And that thing has a big hole in it, and the hole itself, as far as they can tell, must have been caused by some gigantic explosion, like when a galaxy was tumbling into the middle of like a black hole or something like that. And so that's fantastic, and it's pretty impressive to read that kind of a thing. And again, it's an example of how there's really no walls between the sciences, especially in the different types of physics. Right? There's only kind of windows or doors, and so the things that the astronomers are studying relate to the stuff that we are studying as well. Sometimes in direct or indirect ways. And so, I didn't have anything to do with that research, because that's more of astronomy colleagues. Okay. We at CERN, we are interested in the very, very small. We take the smallest possible things and smash them together at extremely high speeds to see what happens.
And if we can go a little bit deeper into this as well, just to put a little bit of a context here. So the actual length, or the actual circumference, is 27 kilometers for the Hadron Collider, and that is below, I think it's France and Switzerland as well, right?
Yes, correct.
Wow, and you guys are accelerating particles at like top speeds?
Well, top in the sense of the highest possible speeds that we can accelerate the particles to, given the other constraints of the experiment, which are physical constraints.
99.999 times the speed of light. I got that right.
Well, yeah, it's a little bit more to be more accurate, it's 99.9999991% of the speed.
Okay, you're the expert. Okay.
Yeah. So I mean, we can back up a bit and really kind of answer that question. It's a really good observation, because it's like, it seems like you hear the word CERN and the Large Hadron Collider and the Higgs Boson and all of these crazy things, and we're creating black holes and all that kind of a thing. And you hear these things, but at the end of the day, it's still sometimes the reason why we do this research is it's still a little bit obscure to some people, right? And so it's important for us to remember that at the end of the day, all that we're doing here at CERN, all of the research that we're doing, all really comes down to a sliced piece of bread. So, for example, for me, I'm sort of an adopted New Yorker now. New York is kind of home base in the United States for me now. So I take a New York bagel, right, and cut it in half, and then cut the half in half, and keep going, right? And eventually you get down to a little crumb. You say, can I cut this crumb? And yeah, you can cut a crumb. And if I use a different implement to see how I'm cutting things, right, then I can get down to like a molecule, right? And then I ask, can I cut, quote unquote, a molecule? Yes, it turns out the molecules are just atoms held together in a particular way. And you ask, can I cut an atom? And the answer is yes, an atom has stuff inside of it, right? There's a nucleus and some electrons flying around, right? But then I get to the electron, and I say, can I cut an electron? And as far as we know, the answer is no. And then you ask, can I also cut, because given our theory, given what we understand about particles, an electron is in fact a point particle. It's zero volume. That's weird. because it can still have properties such as mass and charge and spin, but it has zero volume. And that's very, very strange. But then you ask, can I cut a nucleus? And the answer is yes. We know the nuclei are made up of protons and neutrons. Inside neutrons, there's also smaller particles known as quarks held together. So if you take a proton, all of you are basically made of protons and neutrons. So take an individual proton, and if you were to look close inside of a proton, you'd essentially see three particles known as quarks, and they're held together by these little springy particles known as gluons. And then you ask, can I cut a quark? And the answer is, as far as we know, no. So you see that when you ask that seemingly very simple childlike question, how small can I cut anything? You're secretly asking a much more profound question, which is, what was holding anything together to begin with? So when you do that in a controlled way, you ask this question in a controlled way, and this is really what the history of the 20th century was in particle physics and physics. You get to basically a list of the known fundamental, elementary, uncuttable particles that exist and the ways that those interact, the forces by which those things play together. And it's fairly small number as far as we know now. There are 17 known individual elementary particles, and that's it. And they work. There's a certain number of them that we refer to as matter particles, and they're matter particles. That those matter particles interact via the exchange of other types of particles that are known as force-carrying particles. And one of them you know quite well, the photon. The photon, you're bathed in photons right now, particles of light. And the photon is the force-carrying particle of electromagnetism. And there are other force-carrying particles associated to the other forces that we know of. And so that's really what the game is that we're doing here at the Large Hadron Collider. In particle physics in general. And then what we're doing at the Large Hadron Collider is, so all of this really is related to, again, trying to ask this question, how small can I cut anything? And you're really asking this much more profound question, is what was holding anything together to begin with? And so, what happens is that, and so flash forward to what the project is that we're working on, the main project that I'm working on right now, which is this Large Hadron Collider, right? And the Large Hadron Collider is a 27-kilometer circular tunnel, 100 meters underground here on the border of France and Switzerland. And in this tunnel, we take superconducting magnets that we have to keep colder than outer space. And we put these magnets inside these blue tubes, and these blue tubes run the entire 27-kilometer circumference of this tunnel. And inside these tubes are these magnets, and inside the magnets there are two beams of protons. And like I said, you're all made of protons. And we take individual protons and we accelerate them in this beam. It's kind of think of it like a laser beam, right, or like a science fiction beam, but it's a beam of protons. And this beam of protons, we accelerate it to faster and faster speeds until it gets to almost the speed of light. It can't get to the speed of light, as a lot of your listeners will probably know, right? If you're a particle that has mass, it's impossible for you to ever travel at the speed of light.
Right.
You can get close, but you can never quite get there. And so again, as you pointed out, we accelerate these particles to 99.9999991% of the speed of light. And then at 4 points on this ring, on this 27-kilometer ring, we bend these two beams into each other. They're going in opposite directions. We bend the two beams into each other, and those particles start to smash. They start to collide. And the place where they collide, because they're at such high speeds, you better build a gigantic detector apparatus, because some very interesting quantum field theory magic is going to happen. And so the place, and by gigantic detector, I mean very gigantic. So the one that I work on is called Atlas, and it's 6 stories high.
Wow.
It's 46 meters long. It's like a gigantic soda can tipped on its side as a cylinder and then filled with complicated electronics. And what this detector apparatus really is, it's analogous to a camera in the sense that, your camera, like on your phone, has a certain chip there, a certain CCD, right, that is collecting particles, photons, and as these photons come in, each one of these individual sensors, these readout channels, will get an individual photon, and will be able to write that off and put it into some kind of data storage, right? And then you assemble that in a certain way, and it looks like an image. So in a sense, your camera has a certain number of readout channels where some particle hit it, and then there's a particular, it measures the properties of the particle, in this case a photon, and then it put them all together in a certain geometry. In our case, the detector is about a 100 megapixel camera that takes 3-dimensional photos, and it does this 40 million times per second.
Wow.
So That's the type of camera that we're talking about here, because inside of that gigantic cylinder, you really have a whole mess of complicated electronics, so that when two particles collide right in the middle, these two protons come together and smash, something happens right down there that we'll never see. The thing that we're really interested in is the thing that happens right at the moment of the collision. But we'll never actually be able to see what happened there, because normally if we created a new particle right there in that moment, the particles, it will decay very, very quickly, and then it will spray into a bunch of particles that then hit the detector. And so these particles will be basically kind of spraying out from the collision point. And if you, for example, if you search on the internet for something called Atlas event displays, you'll see these beautiful kind of two-dimensional renderings of the three-dimensional like a three-dimensional image of what happens if the particles coming out from a collision, and see these kind of curving arcs and these kind of blobs of yellow blobs of energy and things like that. And that's really what one of our images looks like. You can never see it. You don't see that with your eyes. This is, of course, like an illustration, but that's a good example of what the collision actually is doing.
And sorry, that would also be the Higgs boson when it was actually detected. It was the same technique and would have come out with the same experiment, right?
Yes, exactly. So that's exactly what we did to discover this particle. Well, let me back up one step, in fact. So the thing that some people might have in their heads right now, a question they have in their heads right now, is that what's the benefit that you get from doing, why do you have to have something so large? What's this 27 kilometers all about, right? And why do you have to get to the very high speeds? What does that matter? It's important because speed correlates to something called kinetic energy, and I think a lot of people know this from their physics courses, right, or just from reading a physics book. There's different types of energy that exist in the universe, right? And energy is more or less the ability to do something, the ability to do work, right?
E is equal to mc squared, right?
Yeah, that's what we're getting to. Yeah, okay. So I'm talking about the concept of energy itself. Energy as a physical concept, right? Is more or less it's the ability to do something. It's the codified ability to make something happen in the universe. And so there's different versions of it. One is potential energy, right? If I put a bowling ball on top of a tall building and I kind of let it sit there on the edge, then I calculate how much potential energy it has compared to the surface of the Earth that's down by the end of the tall building, right? And I can calculate how much damage it would do if it fell off and fell on the sidewalk. There's other kinds of energy, which is kinetic energy. And as you know, kinetic energy is the energy of movement. So if I'm in a car speeding at 50 kilometers an hour, I have a certain amount of kinetic energy. But if I'm speeding at 100 kilometers an hour, I have more kinetic energy. And so that's important for particles, because for particles, there's this thing, as you know, you just pointed out, one of Einstein's most famous equations, right, which is E equals mc squared. And that's a fantastic equation because it points out that there's an equivalence between energy and particle mass. The c part is just the speed of light. It's a constant. You can kind of ignore that part, so that's not really important for this discussion. But what it shows is that E is equal to m under certain conditions in the world of tiny uncuttable particles. And that's important because m, mass, for a particle is not the same thing as the word that we use, mass. We use colloquial, it's like, oh, look at that massive building or something like that. Right. Mass for a particle is simply a property that's put there by nature. It's a number that's put there by nature, and we don't control it. We can only measure it. So, for example, an electron, your body is swarming with electrons, right? An electron has a very fixed mass, m, that's just put there by nature. And again, we can't control that. We just measure it. And it's the same here as it is an electron that's in Alpha Centauri or another one that's just falling into a black hole. It's always the same. And so that we don't measure, we can't control that mass, but we can measure it. And the particles that we know exist have a pretty wide range of masses. An electron has something, has a very, very small mass. And then the something called the Z boson, which is a particle we discovered back in the 1980s, has something like some many orders of magnitude higher mass than the electron. Again, we can't control that; we just measure it. And so this is important because the part of that equation we can control if we work hard enough as humans is the E part. And this is the E part is the kinetic energy of a particle that I can slam into another one. Right. So this is important because because bigger experiments, 27 kilometers rather than say 10 kilometers circular tunnel, bigger experiments allow you to get to higher energies, higher speeds, and then therefore higher collision energies in your collider experiment. And that's important because think about it. If nature has a particle with a mass m that's something very, very high, and we as humans have only ever built an experiment that goes up to a certain collision energy E, we'll never be able to produce this particle in the middle of our detector, produce it in abundance so that we can measure it and measure its properties.
That's so interesting.
So that's really the reason why it was so hard to find the Higgs boson, because no one knew what its mass was. It's really just, there's a lot we could talk about. We can talk about the Higgs boson for probably hours and hours, but the Higgs boson was predicted, the particle was predicted to exist back in the 60s.
Right.
And it took, 40, 50 years for it to be found. Why is that? It's because the prediction of this particle was a fantastic prediction of something called the standard model of particle physics, and this is more or less the standard model is more or less a list of the known uncuttable particles, elementary particles.
Elementary, yeah.
And the way that they exist, right? It's basically a list of that. It's based upon some fairly straightforward mathematical equations. Standard model is the mathematical rules of how all the particles that are down smaller than the atoms themselves, how those work together. And so I call it the standard model, capital S, capital M, and it really deserves that name because it's fascinating. It's more like you can think of it as we say model because it's a theoretical model. It's a set of theoretical ideas, right? It's not just a set series of observations. In fact, it's a set of theoretical ideas based upon mathematics. And as you know, the language of the universe at its basic possible scales, the most fundamental scales, is mathematics. So anytime you really want to understand something with physics, you have to have some kind of mathematical to describe it. Otherwise, no one will take you seriously.
Right.
Throughout the 20th century, it's fascinating because the way that the different kind of observations, somebody would make some observation in a laboratory about some new effect that they see in particle physics, and they'd say, I can't explain that with the current theory. And they'd take it to the theorists, and the theorists would try to understand it a bit better with the math, and they'd say, that could be because of blah blah blah. And then they'd say, because of this, you should do a different experiment, and maybe you see this effect. And so they started putting all these pieces together, and essentially, the standard model of particle physics came out of this century's worth of about half a century's worth of experiments that pointed toward this kind of the structure of everything around us, the way that the individual particles exist, and the way that they kind of interact together. And it's just really this fantastic theory. It's based upon something called group theory and also differential equations. And if you know some straightforward mathematics there, it's a fantastic theory because it just allows you to, if you start with some fairly straightforward mathematics and you kind of turn the crank on these mathematics, it makes very precise predictions as to what you should see in particle physics experiments. And more or less all those predictions are right on. It's fantastic. So back in the 70s, for example, people were like, wait a minute, if our understanding of all of these particle physics observations that we're making at the time, if that understanding is correct, then there should be these extra particles, these things called the W and the Z bosons, the Z boson. These particles should show up in your experiment with a certain mass, above this range.
Does the W particles give the mass to the weak nuclear force? Is that the particle you're talking about?
Yeah, so these W and Z bosons, these are the ones that they don't give mass to it, but what they do is they are the force-carrying particles of the weak nuclear force.
Right.
Yes, you're right there. So those are the ones that are the force carriers for the weak force. And so the three forces of nature that particle physics, that the standard model describes very, very well, are electromagnetism, the weak force, and then the strong force. And the electromagnetism, of course, is mediated, or as the force-carrying particle is the photon. And then for the weak force, it's a little bit weird because it has W plus, W minus, and Z boson. And then the strong force has the gluon as its force-carrying particle. And I didn't come up with the word gluon. Some joke back in the day did, right? Yeah. But it's a good word because it's a really
practical.
Strong force.
And also with
very
the
practical.
Very practical with the Higgs boson, with the discovery of the Higgs boson, I think the interesting thing there was about the fact that there is actually a Higgs field. So if there is a Higgs particle which was detected, I think it's quite amazing to try to visualize, at least for the moment, that there is a Higgs field that permeates through the whole universe. Is that what we are saying? And that's where mass gets rolled up or every time we interact with it. I find that very interesting.
Yeah, so that's in fact the most important thing about this discovery. The Higgs boson, again, just to finish the thought, it's a good question and perfectly timed, right? Because we were talking about how this standard model of particle physics was this wonderful thing that developed over the 20th century, and it kept making these very precise predictions, and they kept being right on. So the W and Z bosons were predicted, and then pow, just in a few years they were found in the experiment, essentially right where they were predicted in the mass. And that was just fantastic, and everybody's like, wow. So the last remaining prediction, if you flash forward to like the mid 2000s, the last remaining prediction of this standard model was the Higgs boson particle. And this thing had been predicted back in the 60s. And so it is a prediction of the standard model, but there's a problem because the standard model says that it exists, but it says nothing about what its mass should be. And that's frustrating because that, if you knew what its mass was, you would have a better sense as to how big of an experiment you should build to find it. So that's why it's why it took so long for particle physicists to discover it. It didn't show up in any of the experiments back in the 70s. And in fact, there's this really fantastic paper from the 70s by some very prominent theorists at the time who were doing some studies on the prediction of the Higgs boson. And at the end of the paper, they have the following quote. It says, we will end this paper with an apology and a note of apology and caution. We apologize to our experimentalist friends and colleagues for having no idea what the mass of the Higgs boson is. And they say, but we wanted with this paper, we wanted to show you, to prepare you as how it might show up in some of your experiments. For this reason, we do not encourage any large experiments just to search for the Higgs boson.
Wow.
And so then, of course, one of the main motivations for the Large Hadron Collider was, of course, to find the Higgs boson.
Exactly.
And it's because since that paper had written, the interest had grown in the Higgs boson, not just because it was the last thing to find, but because the Higgs boson is evident. It's such a weird particle. It's so completely different from all the other ones that we've ever found. For the reasons that you were in fact getting at with us asking about this Higgs field thing. The Higgs boson particle, again, the reason it took until 2012 to find is because we had to eventually build a collider with a high enough energy E, the kinetic energy of these particles, and that was only possible with this Large Hadron Collider at CERN. So we were able to reach something called 13 trillion electron volts, TeV, tera electron volts, at the Large Hadron Collider, and this is enough to discover the Higgs boson. But again, the Higgs boson particle is a fantastic discovery, and of course, some of my colleagues might, don't tell my colleagues I said this, but the Higgs boson particle is not the most important thing about that discovery. Okay. The Higgs boson particle is, in fact, the Higgs boson particle is, in fact, concrete evidence that something called the Higgs field exists.
Right.
And the Higgs field is a completely unique concept that's ever existed in the history of science.
Absolutely.
The Higgs field is essentially an invisible jelly that permeates all of space everywhere all the time. And you don't feel it, but your particles do, because this Higgs field is a thing that allows them to have the concept of mass at all. So again, as we pointed out earlier, mass for particles has nothing to do with volume. It has nothing to do with how much space it takes up, because an electron, as far as we know, has zero volume, and a Higgs boson has zero volume, and a Z particle has zero volume.
Right.
But mass instead, you can think of it as if I'm a particle zipping through the universe and I have a little bit of mass, what it means is that some of my energy as I'm moving around the universe is stuck into a little point by this Higgs field. It's almost as though I'm being dragged through this jelly a little bit. And as I'm dragged through the jelly, a little bit of my energy is stuck into a point that we can measure as mass. And it is the same everywhere in the universe. That if I'm an electron sitting here in Switzerland, I have exactly the same mass as one, that's in Alpha Centauri, right? Because the Higgs field is the same everywhere in the universe.
So it could all just be, we could all just be fluctuations in vibrations, of vibrations, and at different parts of space, right?
Well, deep down inside, that's actually what all of us are. I mean, honestly, if you look down at the smallest possible scale, if you want to ask the question, what are particles really? Particles are not really just chunks of stuff. Again, the analogies, of course, start to break down, right? When we start to make analogies between, our everyday macroscopic world and the particle world, because the particle world follows the rules of quantum mechanics, and the rules of quantum mechanics are totally different, very counterintuitive to what you and I have existed with our entire lives. So it's hard for us to kind of wrap our brains around and think, okay, so when I say a particle, do I mean like a little stone from like a pebble on the beach? And that's not really what I mean. What I mean is that if you look at it closely, a particle closely, it's actually a little vibrating wave packet of probability. Absolutely. And that's totally weird for us to think about, right?
That is so weird.
I can look around me right now, maybe also in your studio, right? You can look around me. There are no vibrating wobbles of probability that I can visualize.
Maybe behind my head, out of my view. And that was a thought at one time, or that was a contradiction that somebody said. That so what happens if nobody is observing the known universe? Does it cease to exist? But James, just to come back to this particular, and I think we should come back here. Would it be possible for us just to go back to the Big Bang and start from there, so that we can come back to where we are now? And you could give us an explanation of the Big Bang and let my listeners know, because yes, we've heard about it, but if you could simplify it for us, phase by phase, that would be really interesting.
Sure. Well, it's interesting too, because the first thing you should think about when you hear about the concept of the Big Bang is like, where did that come from? Like, what really are they talking about there? And no one came up with the Big Bang idea just sort of, they had this sort of a eureka moment where it's like, yes, this is the way the universe came into existence. The Big Bang really is just the logical conclusion that you come to when you observe things about the universe around us. That's really all it is. That's really, as you know, that's really how science progresses, right? We say sometimes that the scientific method is this thing where it's like you come up with a hypothesis and then you design an experiment to test that specific hypothesis, and then you either rule it out or say it has evidence for it. That's not really the way science goes. Science goes because somebody curious looked at something and said, I wonder why that is, right? And so that's really where the most profound discoveries of science come from. And from the Big Bang, it really comes from the fact that astronomers look out into the sky right now and they see that every galaxy is moving away from every other galaxy, and every galactic cluster is moving away from every other galactic cluster in all directions. And it's in fact speeding up at the moment. So if you just look at that, right, and you just make an observation of the universe right now, and you simply just run the clock backwards, in your mind, or run the slider back in YouTube on your mind, farther back toward the moment, farther back in time, at some point this means logically that everything in the universe had to have been packed into a tiny, dense little point that then started expanding. It's just logical, right? If I see, if I turn over and I see a gigantic, explosion with a bunch of stuff flying out, I logically can conclude that all that stuff that's flying out used to be close together. That's really what's happening with this concept. So what we see is everything moving apart from each other in all directions. So we run the clock backwards, and at some point, everything in the universe had to have been packed into a tiny, dense little point that started expanding. And this is the concept of the Big Bang. And the Big Bang is weird because there's so many things so it's not just that simple observation that leads to the notion that everything was packed into a tiny, dense little point. It's strange because we see so many things in the universe right now that we can't really explain if the universe just basically started from sort of a tiny point and then started expanding. It's basically, there's so many things that we can't explain unless the universe was expanded at a sort of different types of rates throughout its history. I don't know how much detail you want to get into here.
Yeah, but really, it'd be interesting. Go ahead.
Yeah, so really, this concept, so the concept of the Big Bang just comes from that. It's like we see everything moving apart from each other, and then we run the clock backwards, and everything had to impact into a tiny, dense little point. In fact, let me get to that other part. We can get to that later if we need to. And so this is important for particle physics experiments because when I say those words, everything in the universe, had to have been packed into a tiny, dense little point. That's a pretty wild thing to say, right? Imagine,
right.
Imagine everything. And when I'm saying a tiny point, I mean something extremely small, like something like 10 to the minus 30 meters, right? That's insane. That seems crazy, right? Because I can't even imagine taking an entire coffee cup and compressing it down into something that's like 10 to the minus 30 meters, something like that.
Yeah, and sorry, when we say Big Bang, James, do you mean? And this is where I just want to get some clarification from you.
Sure.
We're talking about this point that you're talking about, whatever the point is. That point starts with the Big Bang. Is that what we say? Because after that we get into inflation. But I want to just understand between the Big Bang and inflation, this moment, and I think if you could just break this particular phase for us.
Well, so that is the part that's a little bit. In fact, it's not entirely clear what was happening right at the moment of the Big Bang versus when inflation. Mm-hmm. So a lot of people. So if you want to get into a little bit more details. So the Big Bang, it depends on who you're talking to. They will refer to the Big Bang as the moment when everything started to expand, mm-hmm. and other people will say that the moment of the Big Bang was after inflation.
Okay.
So it depends on who you're talking to as to what what you mean by the Big Bang.
Okay.
What I typically refer to as the Big Bang is I just say Big Bang doesn't really matter so much. Where exactly I put the line for where the Big Bang was. What we know is that everything had to have been packed into a tiny point, and then it started expanding. But we know also that it did not just expand at a constant rate. And so kind of what you're getting at is the fact that we know that there's so much in our universe right now that we can't explain unless right at the moment of the Big Bang, it did not just, or right around the moment of the Big Bang, the universe did not just expand at a constant rate, but instead right at the moment of, right at the first part, it did this insane exponential inflation and then slowed down to expand at a much more constant rate. And this, so this inflation part, this is the thing you're referring to as inflationary, and this is inflationary Big Bang theory. And this inflation was so extreme that it's almost impossible to wrap the mind around. Basically, the universe expanded from such a small size to such a macroscopic size in such a small amount of time that it's sort of like if we took a horse and we magically inflated this horse right now to the size of the current observable universe, and we did that in about 10 to the minus 32 seconds.
Wow.
That's what inflation was like at the moment of the Big Bang. It's just colossally insane that this happened, and this happened much faster than the speed of light, and the inflation of space did. But then after that inflation stopped, it suddenly stopped and it slowed down. And in our universe, it's been going at a much slower rate for billions of years.
And you earlier spoke about the four forces of nature, and I want to just bring gravity in here to start with, because I think we need to talk a little bit about gravity. Right. This was also the time that these particular forces, were they equally distributed after the inflation, or is that the reason why gravity is such a weak force? Because for some reason, gravity was not equally distributed.
Yeah, I mean, so I wouldn't say it was equally distributed, but more or less that the interesting thing about the forces of nature, as you're intimating, right? As far as we know, there's only four forces of nature. There could be others, and in fact, that's one of the things that we look for here at the Large Hadron Collider. But as far as we know, there's only four forces of nature, and as it stands now in the universe, we can measure them with great precision. And so, for example, there's the strong force, which is the strongest one that we know of, and this is the one that keeps quarks and gluons held together into protons, and protons and neutrons held together into nuclei, and it's very, very strong. And there's something called the weak force, which, despite its name, is still pretty strong. And then there's electromagnetism, which is photons and electricity and things all around you all the time. And so those, in fact, are all, even though they're not exactly the same strength, they're all kind of in the same range of strengths compared to gravity. And the one that I did not mention is gravity. And gravity right now is so completely weak compared to these other forces that it's basically negligible to us in our experiments here at the Large Hadron Collider. So when two protons collide, we don't even have to think about what the gravitational interaction would be between the two quarks inside the protons. We only care about the other three forces. Seriously, we don't even care about gravity at all because it's so completely weak. Compared to the strong force right now, gravity is something like 10 to the power minus 39.
Wow.
compared to the strong force. It's totally negligible.
Absolutely.
And so you start to think this is crazy, and because in a way you start to think it's like, if you were going to make a universe like this, you would never make this universe like this because it makes no sense. It's very why is the hierarchy of these forces the way they are? And related to what you're saying, we also know that the interesting thing about these forces is their strength. The strength of the interaction that these forces have is not just constant with energy. If you go to higher energy scales, so for higher speeds of particles, things like that, the forces. The force can actually the strength of the force will change a little bit. But this is important because we keep observing throughout physics history that forces that we thought were two distinct, completely different things, if you go to certain ranges, certain scales, they start to be the same force. So you remember back in the 1800s, people thought that electricity and magnetism were two totally different things. And it turned out that they were two parts of the same thing, electromagnetism.
That was Maxwell, right?
Yeah, exactly. Maxwell and some of and his colleagues are the ones that put these all together to realize that electromagnetism was one particular force. Also, we know for a fact that electromagnetism and the weak force, if you go to certain energy scales, those are the same force, electroweak. So electroweak force, we know this exists. And we also have a reason to believe. So there's the notion of kind of unification of forces, right? If we have reason to suspect that if you go to high enough energy scales, electroweak and the strong force would become one force as well. And so you think, okay, well, why should gravity be left out of this? Maybe if we go to very high enough energy scales, we would see that like the electroweak strong force and gravity would come together into one particular force. But that seems very difficult for us to verify right now because gravity is so completely weak than the other compared to the other forces of nature. And we know that these other forces they end up becoming part of the same force. And this leads to one of the key observations about why we're doing all this research here at the Large Hadron Collider and why it's related to the Big Bang. Because what we're really doing when we collide these protons together at such extremely high energies, what we're doing is we're briefly recreating the conditions of the universe as they were just a fraction of a second around the Big Bang, after the Big Bang. And that's important because and this relates to energy and temperature, right? You know that energy and temperature are related.
Right.
And if I have a particle that's going to very, very high energy, it gets up, goes to very high speed, it can get to a very high energy, and then I smash them together. And when that smashing happens together, it happens at a certain energy. If I take a thermometer right now and I put it out in outer space, the average temperature of the universe is very, very low. The universe is huge, and if I put the thermometer in outer space, it's like 2.7 Kelvin or something like that. That means that the overall average energy of the universe is extremely low right now. This was not always the case, because if I take everything in the universe, I run the clock backwards and I smash it into a tiny, dense little point, the size of a pea, the size of a speck of dust, the size of an atom. That the temperature of everything goes extremely high. Particles don't like it when you smash them together, and they start to vibrate. And they start to radiate, and different, they take on different forms, and energy and mass get, kind of just smushed together, and the average temperature goes very high. So if we want to study what was going on right at the moment of the Big Bang, or just a few, fraction of a second after that, we need to recreate those conditions in a laboratory. Obviously, we can't really recreate the Big Bang because we don't have all the stuff, but we can recreate a small part of that in the laboratory, and that's really what we're doing. And that's important because if we do that, and it allows us to recreate those conditions and study the conditions, and it's possible for us to find particles that would help us that could have, in fact, very high masses m that were only existed in abundance right at the moment of the Big Bang, and that then as the universe started to expand, they sort of died out in a particular way.
That's
and the
so
way
interesting.
They died out, they give us, the way that they died out, they then give us sort of an imprint on everything that we see in the universe now, sort of like a code or like a puzzle that we have to, work backwards and try to recreate and see if we can figure out what was going on. So that's one of the reasons why, if we really want to understand everything about the universe that happened at the Big Bang, we need to go to bigger and bigger machines, much larger than the Large Hadron Collider. And eventually, we could go back far enough that in principle we could reach a point at such high energies so far back toward the moment of the Big Bang that maybe all of the forces in nature would turn into one force. And that would be a fantastic discovery.
That would be stunning. And I think that was also the time when all of matter would have come into being. But is it the time to then ask the question about antimatter or supersymmetry? Because if there was matter, like you said, that was created, is there, what is the fact with antimatter, and does it, have you able to detect it as yet?
Yeah, so antimatter is a fascinating concept, and it's not as exotic as you might think it is, because antimatter we know exists quite well, and in fact we can. Let's put it this way: we know that. So when we say antimatter, what we're referring to in a very kind of basic sense is if you take a particle with a given charge, and it should have an opposite particle with the opposite charge. It has all the same properties, but it has opposite charge. So for an electron, the antimatter particle, the antiparticle of the electron, is something called a positron, because by convention the electron has a charge that's -1, an electric charge that's -1. So then I flip the charge on that, a +1, the same particle, same everything. This means that it has a +1 charge, and it's called a positron. So in that case, this is the positron is the antiparticle of the electron, and all of the known particles that have charge, they have known antiparticles. So when we refer to antimatter, that is, it depends on who you talk to, but typically we refer to something that would be more or less, could you create some kind of stable, some kind of stable anti-atom in a way, and that you can measure its properties. So, for example, instead of a hydrogen atom, which is a proton with an electron going around it, could you create an antiproton with a positron flying around it? And in this sense, this would be antimatter. But antimatter is not such a, so it's not such an exotic thing in that sense, because we know that antimatter exists. And in fact, in very small experiments, you can demonstrate, you can create positrons, for example. So we create these antiparticles all the time. But the puzzle comes from the fact that, think about our universe just from first principles, right? One of the biggest concepts that governs everything we do in physics is the notion of symmetries, right? And so these are kind of analogous to formal symmetries, like the symmetry of a circle. If I rotate a circle and around its middle axis, everything stays the same. And I can do the same with like a spherical ball. I can then a line has a different type of symmetry, and it's not symmetric in certain directions, but other directions too. So I can also think of it in terms of just in terms of the elegance of the universe, right? Why should our universe have only a bunch of matter in it and not any antimatter? Because if I start from zero, if I start from the very moment of the Big Bang, why should I have a distribution of things that's mostly matter particles and not antimatter particles? It kind of makes no sense, and it sort of seems it's asymmetrical. Why would we have a universe that's so asymmetrical? So we think that at the moment of the Big Bang, everything was symmetrical. There were an equal number of an equal number of matter particles and antimatter particles. But then at some point, something happened. There was a small imbalance that came from somewhere, so that there were a tiny number of a slightly larger number of matter particles than antimatter particles. And as you know, when a matter particle and an antimatter particle meet each other, they annihilate. So if I take an electron and a positron and I get them close to each other, they'll zap each other and turn into a flash of light. And so they annihilate and turn into energy, or turn into photons, something like that.
Right.
So that really should have happened, when at the moment of the Big Bang, when everything started to expand. If you had equal numbers of matter particles and antimatter particles, as everything started to zip apart, they would have found each other and annihilated into just a complete sea of energy. And we would never have seen, we'd never have particles as we know of. We never have matter as it is now. But something happened so that there were basically, that did happen. All of the matter particles and the antimatter particles did annihilate and give a bunch of energy, but there happened to be just a smaller number of matter particles that hung around. They didn't have any antimatter particles to annihilate with, and they started to expand and turn into eventually atoms and molecules and big things, and eventually us. So something happened right at the moment of the Big Bang to create this asymmetry. We still don't know where that asymmetry came from. It's one of the biggest open questions that people are studying here.
And that's so interesting, because post that, the actual proof of the Big Bang, or everything that you've just explained to us, credit has to probably be given to Penzias and Wilson for having discovered the cosmic microwave background. And I don't think they intentionally discovered it, though. It was by accident, right? They had something on the antenna of the roof, and could you tell us about that? That's so interesting as well.
Yeah, as far as I remember, they were doing they had some kind of like their radio telescope, right?
Right.
And they had some kind of persistent background noise, and like, what is this noise? You know, it was a very precise instrument, and they're like, what is this? And they thought maybe it was, you know, if I remember correctly, maybe some birds were getting into it or something like that. And they thought, you know, there was some
pigeon droppings,
some dust or pigeon droppings. And so then once they ruled out all the other possible sources where this persistent background come from, and then they thought about it more critically, and they realized, holy cow, what we're actually detecting is this constant sea of very, very low energy radiation, low energy photons that have been coming to travel toward the Earth for nearly 13 billion, you know, almost 14 billion years to finally arrive at us. And they discovered this thing called the cosmic microwave background, and it was really, you know, it was one of the most profound discoveries in the history of science.
So, James, with the cosmic microwave background post the Big Bang, I just want to get to the fact that progressively the universe at that time of the Big Bang would have been in a very simple state, or we could say that it was less complicated, if you could, because what I'm trying to get here is I want to get to entropy and how complexity increases with the passage of time. Now, considering where we are today after all these years, how would you look at the concept of entropy where we are today? Because we then have to talk about how is probably the universe going to end. How would you look at this?
Yeah, there's a lot of questions in that one question. We could probably spend an entire episode on each one of these subjects.
All right.
Yeah, it's fascinating because, well, to focus in on one part of the question first. So in terms of what we suspect happened through the history of the universe, starting with the Big Bang, you know, there is this concept in physics, as you know, entropy. You know, the laws of thermodynamics. This notion that disorder increases as time goes on, right? But obviously, that's not entirely true on small scales, because if that were true, there would have been, you know, some structure at the beginning of the universe, and then eventually everything would have just decayed into a mess of blah, right? But that's not true, because clearly over the billions of years that the universe has existed, you know, stuff started from a kind of sea of particles, and they started to coalesce due to different forces and gravity pulling them together, and, you know, they made into, you know, planets and rocks and dust and galaxies and, you know, real structures that we observe right now in us, right? And so it almost seems at first glance that that's somewhat contradictory to the notion of entropy. But, you know, entropy on the scale of the universe is really only valid, again, on the scale of the universe. Anytime you talk about entropy, you have to define exactly what you mean by your, you know, the parameters of the scale and the parameters of your experiment. So on the scale of the universe, you can argue that over the long term, yes, entropy is increasing. On small scales, individually, you can have pockets of order that come into existence, obviously, and those are still totally okay with the laws of entropy as we know them. But at the moment of the Big Bang, it's important to understand that this cosmic microwave background radiation, as you pointed out, right when the universe started to expand, all this stuff was packed into we suspect that everything was packed into such a small, dense point that, again, the concept of particles themselves was not so clear. So if you in fact, some of my colleagues here tried to study something called a quark-gluon plasma. And this quark-gluon plasma is a consequence of the weirdness of the strong force. The strong force is strange compared to the other forces that we know of, because it's the opposite from, for example, electromagnetism, which, as you know, is a 1/distance force. It's an inverse squared law, right? So if I have an electron and a positron, and I hold them half a meter apart, they feel a certain electromagnetic force between them. And then if I take them 1 meter apart, they will feel less force. And if I take this electron and take it to take the positron to Alpha Centauri, then the force will be very, very small. It's still measurable, but it's still calculable, but it's very close to nothing. But that's totally different for the strong force. For the strong force, it's completely opposite. If I have two quarks that are held together by the strong force, and, you know, let's say that I'm God, I can say this as an atheist, I'm God, and I'm going to try to pull apart these quarks. And I start to pull the quarks apart. The strong force says, no, I'm going to increase the strength of the force between them. So as they get farther apart, the strength of the force goes up, And you say, but then you say, well, wait a minute, I'm God. I can do whatever I want to. You start to pull the quarks apart. The strong force says, no, I'm going to make it harder for you to pull them apart. And you say, but no, I'm God. I have to win. And you pull them farther and farther. The strong force says, okay, just to spite you, because I am nature and I'm always going to win, I'm going to create a quark-anti-quark pair out of the vacuum and put it right in the middle of the distance that you pulled these apart just to spite you. So that's the nature of the strong force. It always wins. And it always, as a result, we can never find a free quark floating around by itself. We've never observed one of these things. But then if you run that the other direction, what if I take two quarks and I smash them closer and closer together? What if I put them so close to each other, that means that the force between them should in fact get lower and lower.
Right.
And eventually it could get to such a point that the concept of particles makes no sense because there's no friction. Basically it's a completely frictionless liquid. It's the perfect liquid where you have a quark. The concept of individual particles disappears, and you have this sort of like perfect liquid of pure energy just kind of frothing around.
Right.
So at the moment of the Big Bang, we suspect that was what was going on. The concept of individual particles didn't make much sense. Then as the universe started to expand, for the first, so we had this inflation, and then we started to have this. Then we had this kind of the Big Bang idea, where everything just started to expand at a more kind of constant rate, or a constant acceleration, more rate. And then it did this, in fact, but still, after the moment of this Big Bang, for in fact a few 100,000 years, it was more or less everything was still kind of in a soupy relation. You did have individual particles, but in fact they were still pretty close together, so much so that any time one of them wanted to, say, radiate, wanted to get rid of some energy, like to send off a photon, it would immediately get absorbed by a nearby particle. For example, so if I'm an excited electron, or I'm an excited atom or something like that, and if I'm an excited particle and I'm kind of bumping around and I'm giving off radiation, that would immediately be absorbed by some other particle, just immediately. There's no way for it to go anywhere. There's no room for it to go anywhere. And it did this for a few 100,000 years. And then at some point, about a few 100,000 years, suddenly everything expanded just far enough so that there was room. There was space for photons as they started getting scattered from other particles. They actually had some room to fly, and as a result of that, suddenly the universe, which was previously opaque, became transparent. Suddenly, in the sense that if I were somehow magically, I had like a telescope for the first few 100,000 years of the universe's existence, I would never be able to see anything because there's no photons free to be able to get into my magic telescope. But finally, after a few 100,000 years, something happened. It just got big enough, the universe got big enough that there was room for photons to fly. And suddenly, as photons could fly through free space, then the universe became transparent and you could see things. But as the universe kept expanding, it kept doing this. It is expanding right now. It was doing this for 13 billion years. It meant that there were going to be some photons that would start to fly off from this last scattering surface that would fly for basically billions of years. And so one of the photons from some other part of the universe, right, would have started right at that moment a few 100,000 years after the Big Bang, and it would start to fly toward the area of space where where the Milky Way would eventually coalesce, and where eventually the solar system would come together, and eventually the Earth would come together, and eventually protozoans would start to evolve, and eventually humans would exist. And then one of those photons, eventually 13.8 billion years ago, would suddenly smack into Penzias and Wilson's apparatus to point out, it's like you are completely constantly bathed in these photons that have been traveling since since a few 100,000 years after the Big Bang to finally reach us.
I could stand and applaud. That's such an amazing description, James. That's such an amazing description.
It's just so constantly humbling to be a physicist, right? And just a curious human being, right? So when it's just humbling to realize that as humans, we have the capacity, we have the ingenuity and the innovation to come up with experiments and ideas to test this, to really, and to conclude that, you know, if you've seen this, I urge everyone, I think you probably have, but I urge everyone to get online and to search, you know, cosmic microwave background image, and this wonderful oval image.
I've seen
it.
Yeah,
with the little kind of blotches of blue and yellow and red.
I actually have a poster of that in my room.
It's just stunning every time I look at it, because that is essentially, that's the closest we as humans can get. That's a baby picture of our universe.
Absolutely.
And it's just so you know, it's just humbling.
It's humbling, yeah. It's humbling.
Humans can do this.
Right. And you were mentioning that for the first, I think you said 100,000 years, till the photons actually got out of this mist. So no matter how far we go back, that is in a way the universe holding its secret, right? We would never able to see past that barrier of 100,000 because there was no light coming out before that.
Correct. Yeah. And if there were, you know, again, if it was immediately absorbed, right? So that, you know, you can say that the concept of light, you know, the concept of electromagnetism and photons, they did exist, but they weren't free. They couldn't get anywhere. They couldn't fly anywhere. So for us to literally see back farther than that, it's basically impossible.
And
which is why it's important for us to, you know, to design these higher energy experiments so that we can recreate the conditions closer and closer to the moment of the Big Bang, to better understand what's going on, because there's no way for us to ever actually see what was going on right then.
And you mentioned a little bit earlier about entropy, and as you say that we move into nature by nature, we move more into chaos. That is also connected with the arrow of time. So that makes it difficult for us to actually. Well, I think what you guys are telling us is that you theoretically can move in both directions, right? Even though we have an arrow of time because of entropy. The formula or the theory does tell us that we can move both ways.
You mean both ways in time? Or
In time.
Yeah. Well, that is one of the biggest open questions of science, and it has been for a long time. And it's not just the biggest open questions of science; it's also the biggest open question of speculative science fiction, right? So the best science fiction, of course, is informed by real science, right? And it takes it into more speculative ways. And so, you know, anytime you watch a TV show with somebody traveling through time in some kind of, you know, magic phone box, right? It's a really nice image, and it's really, you know, kind of a nice metaphor or a fun thing to look at. But to really do time travel, especially reverse time travel, in principle, it's possible. But from all of, you know, when I say in principle, I mean both from a physical perspective. You know, we can in principle come up with some practical, I don't want to say practical, we can in principle come up with a physical device that would allow someone, if all the properties were correct, it would allow a human to travel backwards in time. To do so seems basically impossible for our civilization at the moment. We can talk about that in detail if you want, but it also in principle is possible because, yeah, as you pointed out, time is, you know, as we know from Einstein, you know, from relativity, time is not so different from space. You know, anytime you, you know, for example, if you want to make a coffee date with someone, you have to specify. It's not enough to specify 3 points in space, right? You and I live in a 3-dimensional space, unless there's other hidden dimensions that we can't currently observe. You know, it's not enough to specify 3 dimensions of space. You also have to specify what time you meet. Otherwise, there's no way for you to meet for coffee. So this means that, in a sense, time is just another coordinate, you know, by which we can define how an event occurs, how something actually occurs. And so in that case, time is very similar to space. And Einstein pointed out that if you look at it more closely and the mathematics behind it, especially when you go to the extreme things that the universe has in store for us, you and I can't really experience this so much, in a little bit, but not so much. If you take, for example, a particle going at very high speeds, the notion of time and space being separate totally breaks down. Time and space are very much 2 parts of the same thing, which is more of a space-time continuum. And that's fascinating, because that's interesting, because what it means is that, you know, at the extreme parts of the universe, if space can be bent, and we know it can, you know, the general relativity, which is the best description we have as to how gravity works on large things, general relativity is, in fact, a description that when you have a bunch of mass or energy density in one particular, in a certain type of space or volume, it creates more or less a warping of space. And that's, for example, how you have, say, the moon that is going around the Earth all the time, is because it's constantly falling around us into you know, the Earth is creating this big, this kind of divot in the, or kind of a like in space, and then the moon is sort of following around that. And so, but if space and time are two parts of the same thing, space-time, if space can be bent, then time can be bent too. And we know that we in fact can observe this in smaller ways all the time. So, for example, the GPS system in your phone, it would be off by several dozen meters if we didn't correct for the redshift of the signal that has to, because these GPS satellites are actually quite high up into higher Earth orbit, and the amount of time that it takes them to get these signals to come from far enough away where the gravity is markedly less than it is down here, that has to be corrected for. Otherwise, the accuracy would be off by several, I think maybe even dozen, maybe even kilometers. Anyway, so you have to correct for this. And for example, so we know that time can be bent, but in principle, for us to be able to travel backwards in time, we would probably have to go to extreme lengths to be able to bend the space-time continuum, so that some point far, far back in time would be able to touch ours in some sense that you could move across. Like, this would be, for example, if we could somehow right now, our civilization
could connect two black holes and form a wormhole, right?
Exactly. If we could somehow connect two black holes, or we might think, let's not just find two black holes and then drag them next to each other. Why don't we just take a star and we can collapse the entire star somehow into a space the size of about a coffee cup, and then we somehow control this space and blow it up to the size of a human and create a wormhole, and somehow figure out how to choose what point in the time continuum we'll be going to.
There were a few people who had this concern about CERN. I'm sure you know about it. That they said that, well, what's going to happen at CERN is that we're going to create a black hole and we're going to expand all disappear into it.
Yes, that in fact was a hysterical story in the news, and like a lot of news stories about the extremes of science, it's sort of underneath it has a kernel of a very interesting idea, but then it gets blown up into a very strange place. It's related to the fact that, well, in fact, it's one of the most fascinating things we can study here. We don't see any evidence for this object so far, but in fact, we can look for something called a quantum black hole, or a mini black hole, or a microscopic black hole. And this would be an object that we could create in our collisions that would technically satisfy the same equations as those of a gigantic supermassive black hole up in space, something that would swallow entire galaxies, but it would not be the same thing as one of those black holes, because it's tiny. Even though we say that our experiment here at the Large Hadron Collider, we use the highest energy ever used in a collider experiment, the universe has much higher energy things going on all the time, even particle collisions. So, for example, there are particles coming in from outer space, cosmic rays, that smack into the atoms in our upper atmosphere all the time that are at much, much higher energies than the Large Hadron Collider. So, what we mean is that when we collide two protons together at high energies like this, we in fact, one of the things that we can search for in our data is this thing called a quantum black hole, or some kind of like hyperdimensional graviton. And this would be fascinating, because if we were able to find one of these things, it would help us possibly explain, if nature had one of these things in store for us and we discover it, it would possibly help us explain why gravity is so weak compared to the other forces of nature. So, for the following reasons, so if we were to, if we were to collide two protons together at high energies, it's possible that we could coax this little hyperdimensional graviton thing into existence for a small amount of time, and like I said, gravity is extremely weak compared to the other forces of nature, something like 10 to the minus 39 compared to the strong force, would give it a value of 1, right? Possibly that could be, and that doesn't really satisfy our kind of notions of elegance, right? Obviously, the universe doesn't have to be elegant to humans. The universe just is, and it doesn't matter. It doesn't care if we think it's elegant or not, right? But it starts to make you think, it's like, why would gravity be so weak, so weak compared to the other forces? One of the ways is that maybe gravity is just as strong as the other forces if we were able to measure it in more than 3 dimensions of space.
Yeah, so maybe
you and I only exist in 3 dimensions of space, but maybe the extra gravity that we're missing is leaking into spatial dimensions that are invisible to you and I.
So listeners, as we promised, I'm sure a lot of you have been enjoying this conversation, and we would like to take this further into part 2, where we go deeper into these questions and touch on some of the most exciting topics currently out there, pushing further into the boundaries of human thought, reason, and science. Thank you for listening and hope to catch up with you in episode